Hi everyone, my name is Kartik Lakhotia and I'm going to present our paper titled Refine Coarse-grained Independent Tasks for Parallel Tip Decomposition of Bipartite Graphs. Now, bipartite graphs are a natural representation for systems that have relationships between two different types of objects. So for example, in this figure on the right, one of the classes is users and the other classes is products, and the edges in the graph that depict which products were purchased by which users. Now, bipartite graphs arise in several other domains as well, like user rating networks like IMDb or group memberships on forums like Reddit or social networks, etc. Now, dense graph mining can reveal interesting structures in these systems. And typically for graph structure data, triangles, cliques, or pseudo cliques are used for mining these dense subgraphs. However, bipartite graphs do not have triangles or cliques. Hence, butterflies or 2x2 bicliques are used instead. And butterflies is the smallest non-trivial dense motif in a bipartite graph. And basically, it consists of two pairs of fully connected vertices as shown by these red colored edges in the figure. Now, butterfly-based analytics have applications in anomaly detection, recommendation, etc. Now, per vertex or per edge butterfly counts only provide a very localized view of density around individual entities in the graph. To obtain dense subgraphs, instead, researchers have proposed structures called K-tip. A K-tip is essentially a butterfly dense subgraph where every vertex participates in at least k butterflies within the subgraph itself. And tip decomposition, which is the subject of this paper, is the analytic that computes k-tips for all possible values of k, revealing an entire hierarchy of varying density subgraphs as shown in this figure. Now, one thing you'll notice is that each k-tip completely overlaps with all the less dense k-tips. So for example, 3-tip is completely contained in 2-tip, which is completely contained in 1-tip. So the concept of tip number is introduced to efficiently store this hierarchy. So instead of storing all the subgraphs for each vertex, you just store one number, which represents the largest k for which that uh, vertex exists in a k-tip. So it naturally exists in all the less dense k-tips. So for example, vertex U2 here has a tip number 3, so it exists in 1, 2, and 3 tips. Now, in current practice, bottom-up peeling is used to construct this tip decomposition hierarchy. In this approach, vertices with minimum butterfly count are deleted, they're assigned a tip number, and butterfly count of other vertices is updated. So this entire procedure is called peeling the vertices. The hierarchy, in this approach, the hierarchy is constructed one level at a time and in an increasing order of density. So for example, in this figure, you can see that we're first peeling vertices with tip number 1, then you're peeling vertices with tip number 2, and then you're peeling vertices with tip number 3. Uh, Now, the problem with this approach is that, first of all, it's computationally very intensive because when you have to update the butterfly counts of other vertices, you have to mine butterflies incident on the peeled vertices. And this requires traversing wedges in the graph, which is quadratic in the vertex degrees. And the second problem with this approach is that it is also tough to parallelize efficiently because tip decomposition hierarchy typically has a lot of levels. For each level, you may actually require multiple iterations to construct that particular level itself. So overall, it leads to too many iterations, and each iteration is sequentially dependent on the updates in previous iterations. So you cannot parallelize workload across the iterations. So you have to synchronize after each iteration, resulting in huge amount of synchronization and the poor parallel scalability. So for example, in this table also, you can see that the parallel version of bottom-up peeling running on 36 cores hardly achieves 2x speed up on maybe one of the data sets over the sequential version of bottom-up peeling. Now, in this context, this slide summarizes the accomplishments of our paper. So first and foremost, we propose a novel two-phase peeling methodology, which allows us to exploit parallelism across the levels of the hierarchy, not just within. And this results in a drastic reduction in synchronization and improved scalability. And tailored to this approach, we also propose some optimizations to improve computational efficiency. And we show that we are able to decompose some of the very large data sets that the existing algorithms cannot. And overall, our techniques with the speed up and with the novelties in the algorithm, we significantly advance the state of current practice in this direction. Now, this slide gives a brief summary of our two-phase peeling approach. So for details, I would refer the audience to our paper. The key idea here is that instead of one-shot construction of all levels in the hierarchy, we first divide the hierarchy into few partitions, each partition consisting of multiple levels. And in the second phase, we define these partitions, or we process these partitions to construct individual levels within them. In other words, instead of computing the tip numbers directly, we first compute upper and lower bounds on the tip numbers of vertices, and then we refine these bounds to compute the individual tip numbers. Now, the first phase, which is coarse decomposition, which partitions the hierarchy, uh, does so with very few iterations because it is creating very few partitions as compared to the number of actual levels in the hierarchy. So it requires very few iterations and very little synchronization. And in the second phase, each of these partitions are completely independent and processed concurrently. So the threads, they don't actually need any global synchronization for this particular process. So overall, we can do this entire decomposition with very little synchronization and also exploit the parallelism across the levels in both phases. Now, tailored to this approach, we also propose some computational efficiency optimizations. I think the main optimization, which is what we call hybrid update computation, is based on the fact that in the first phase, which does most of the work in the algorithm, each iteration is peeling vertices within a broad range of tip numbers. So sometimes you may peel a lot of vertices. And what we also notice is that butterfly counting is actually parallel and much more efficient than peeling the vertices. So if you're peeling a lot of vertices and have a lot of work to do corresponding to computing the updates, so instead of doing the peeling procedure, we just remove those vertices from the graph and recount the butterflies of remaining vertices using the butterfly counting algorithm. So this saves us a lot of traversal and without actually sacrificing any of the parallelism. Now, we test our approach on a 36-core dual-socket Intel Xeon server and compare it against sequential bottom-up peeling and we recently proposed pair butterfly framework. And we tested on several datasets with trillions of butterflies and hundreds of trillions of wedges. And we decompose both the vertex sets individually in these datasets. So the U vertex set is the one which has higher complexity of decomposition. Now, this slide shows the results for execution time. So the lower the execution time, the lower, the better the algorithm is. And you can see that this dark blue colored bar, which is for our algorithm called receipt, this is smaller than all of the smaller than the baselines in all of the cases. And overall, approximately 2 orders of magnitude improvement over the baselines. And one of these data sets, TRU, we can process it in around 45 minutes, whereas both the baselines, they cannot even process it within 2 days. Again, this slide shows the amount of synchronization rounds. Each synchronization round is basically one parallel peeling iteration that incurred by the algorithms. And overall, we achieve up to 3 orders of magnitude reduction in synchronization, which is the key to improve scalability. And lastly, this one shows the reduction in wedge traversal. And due to our computational optimizations, we achieve up to 64x reduction in the wedges traversed for that large data set that we could feasibly process. So with this slide, I conclude the presentation. So to summarize, we propose a novel 2-phase approach for tip decomposition, which allows us to exploit parallelism across the levels of hierarchy, not just within. And tailored to this approach, we also propose some optimizations that improve computational efficiency and allow us to decompose some large data sets that baselines cannot. And our code is freely available at this given link. And there are several directions for future work in this area as well. So the first natural direction is to generalize this approach for peeling edges, which is used for wing or bias decomposition. And it's been shown that it gives better quality subgraphs than tip decomposition. So we have made some advancements in this direction and have seen some promising results as well. And secondly, because it takes so much time to compute the decomposition, it is natural to scale it on distributed memory systems where you can get more computational resources, potentially more parallelism. And this approach might be suitable as well because we are creating these independent tasks which do not need to communicate with each other. And lastly, we would also like to explore some system optimizations to improve the cache and memory performance, which have been shown to affect graph algorithms in the past. Thank you.